Good morning or afternoon, everyone. My name is Elisa Bates with OU0 and the Warning Decision Training Division. I am joined by Jill Hardy, also of WDTD. Thank you all for joining, and let's get started. So today we are honored to host our last webinar by Patrick Burke and Pat Skinner of the National Severe Storms Laboratory. Patrick Burke is part of the management team for the NSSL Warn on Forecast group, and with a background as a National Weather Service forecaster, he specializes in outreach and real-world applications. Prior to NSSL, Patrick was a lead forecaster at the Weather Prediction Center from 2015 to 2020, and is now in his third year as Warn on Forecast program lead. Pat Skinner is a research scientist at CRO NSSL with a background in severe thunderstorm dynamics and prediction. He has worked with the Warn on Forecast project since 2016 and has worked extensively with visualization, evaluation, and interpretation of WoFS guidance. Together, they will be presenting on strengths, weaknesses, and real-world applications of the NSSL Warn on Forecast system, or WoFS. All right, that's it for me on logistics. So Patrick, take it away.
All right, thank you for that introduction, Elisa. Appreciate it. We're glad to be here speaking to you all who have interest in the Warn on Forecast system. We're here to talk about the Warn on Forecast system and just give you a sense of where we're going in the next 45 minutes or so. I'll give a presentation for 20 minutes, and then Pat Skinner will lead us in a demonstration of the WoFS web viewer, and we hope to have plenty of time to get to your questions towards the end. So let's just dive right in here. There's always a lot to talk about when it comes to Warn on Forecast. And I thought instead of showing you, model workflow diagrams or specifications, let's just look at a case study that really illustrates what the Warn on Forecast system is all about. So this is May 20th from last year. This is the Gaylord, Michigan tornado. So we're going to see a discrete supercell track across northern lower Michigan. And this slide requires a little bit of setup, but the columns here are organized by time. So we have the 17Z run of WoFS, the 18Z, the 19Z in the different columns. And WoFS actually puts out a new forecast suite every 30 minutes, but just for simplicity, I'm showing the hourly ones here. Across the top is the probability of mid-level updraft rotation exceeding some threshold. I'm using kind of a mid-range neighborhood there. And the bottom shows the MRMS observed reflectivity at the time that the model was initialized. And this is one of the key concepts that we'll hit hard in this presentation, is that WoFS performance should improve the more observations that we've assimilated into the system as time goes by for any individual thunderstorm. And so our data assimilation cycle is 15 minutes. This storm at 17Z had existed for about 30 minutes, so that's 2 assimilation cycles. By 18Z, we've got 6 assimilation cycles, and you see that the probability swath, the values come up into the mid-range, and it's a little bit more focused. By 19Z, where we've been assimilating this thunderstorm for over 2 hours now, we have a really focused probability swath for updraft rotation at about 70% in value. So the performance keeps honing in on that storm as we go along. And on this next slide, I attempt to show how we think forecasters could use this information even if the WoFS forecast isn't perfect. So now I'm looking at the 1830Z and 19Z forecasts in the right-hand columns there. And I pulled out an individual member from the 1830Z forecast showing a loop of reflectivity and the updraft velocity swath that it's leaving behind. And the city of Gaylord is labeled on these plots as the blue circle. The point being here, at 1830 to 19Z, that's a little over an hour's worth of lead time, or 30 minutes for the 19Z run on this event in the city of Gaylord. And if you look at the 1830 plot, the WoFS probability swath was pretty far to the north of the city where the most likely values are. But if we look at the max percentile, so what's the strongest updraft velocity value of any member in WoFS at 1830Z, it shows that the worst case scenario is sitting on the south end of that probability gradient, right over the city. So as early as an hour before the event, there was this signal in a minority of members that a worst case scenario was at least possible. If you look at the 19Z forecast, the swath is still north of the city, but it has trended to the south. And although the maximum percentile is displaced to the north, it does show that the greatest values occurring at about the longitude of Gaylord. So I think that it would be reasonable for forecasters to take this information, adjust it for the true location of the storm on radar, and perhaps gain some lead time, whether it's in a polygon or in some sort of pre-warning activity communicating to your partners. And that's exactly what we saw happen on May 16th in 2017. This was really the first year that the War on Forecast system became viable as a real-time tool for testing. And we had Pat Skinner was embedded at the WFO in Norman on this day, a couple of supercells coming out of the Texas Panhandle, and WoFS gave signals that were very much like the Michigan storm. And so Norman issued a special weather statement that had some pretty unusual wording for that time, stating there's a high probability that tornado warnings will be issued later. That statement was sent 60 minutes prior to the first warning and about 80 minutes prior to when Elk City, Oklahoma was impacted by an EF2 tornado. And you see the quote there from Todd Lindley, the Sioux at Norman, and I think that really sums up what WoFS is doing for forecasters at this time, is giving confidence to make these kinds of statements with greater lead time and greater confidence in the event. And you see the emergency manager was able to sound the sirens about 30 minutes ahead of the tornado strike, and that's certainly above the national average for your average tornado warning. I did want to emphasize that WoFS is really, while it looks like a model and it looks like an ensemble, and it is, it's really the first of its kind in terms of its rapid pace. It's the first ensemble designed specifically to make probabilistic predictions of individual storms and their individual hazards at the pace of severe weather operations in that watch to warning kind of time frame. And a key ingredient to being able to do this is focusing on the visualization, designing these plots that are easy to produce and then easy to interpret in real time in those fast-paced warning operations. So I'm showing a few examples of the unique plots that have been designed really in collaboration with forecasters in our test bed since 2017. You see the tropical cyclone multi-hazard plot there. And in the upper right, the paintball plots, which have become some of our most popular products. And honestly, there's a lot going on there, and it can look overwhelming at first. But the more you get practice looking at these, you'll see different things emerge, such as storm mode, where you have supercells early on in eastern Kansas and some left splits moving up there, followed by some Boeing segments towards the end of the run. And you can even infer probability where there's a lot of overlap between the different members. So this would be one of the first products that I would go to get a sense of what's happening in a new WoFS run when it comes out. And then in the lower left, I've tried to summarize what have been the emerging common best practices at Weather Service offices. And I should say that this is still an experimental system. It doesn't run every day, and we're discovering every time that we run new ways to use the system. So we hope to hear more and more of that feedback from you all. But in general, WoFS has been leading to greater effective lead time, like we saw with the Norman case, through some IDSS activities, kind of pre-warning or in between the watch and warning. And then at the national centers in their mesoscale discussion, providing event context. And in particular, because we're a 3-kilometer system and we're not modeling individual tornadic circulations, some of the best value has really been seen in heavy rainfall cases and convective wind. So just kind of thinking about how to use the system in operations, I think for a first-time user, the menu structure can look overwhelming. There are a lot of products and they're updating entirely every 30 minutes. But if we break it down here, there's really only 7 different types of product to become familiar with, and 4 of them on the left there should be familiar as part of any ensemble system. The ensemble mean we tend to reserve for the environmental plots because taking a mean of individual storm objects loses a lot of precision that's available in other products. So we have our member viewer for that, for you to examine each individual member, find which ones are best initialized, look at different emerging scenarios and how frequently they occur. And then really the bread and butter of probabilistic prediction, the probability and percentile plots. We have those scattered throughout the web viewer for the individual hazards, for additional hazards like lightning. And so you'll find those in many cases. And for the probability plots, we have to choose a neighborhood each time you load one of those. So you might want a more specific, smaller neighborhood when confidence is high in the event. When confidence is low, or maybe it's pre-convective initiation, a large neighborhood is better because that'll boost the signal, but you lose some precision. And I think Pat Skinner will go over that in his demo a little bit later on. But those are the ensemble products there. And then on the right-hand side, we have some specialty things. Our forecast soundings plot every member on the same plot. There's some nice scatter plots where you can see the distribution among different PBL schemes of the 18 members. So there's some unique things on those plots. And the paintballs we already talked about, but we also have paintballs for the individual hazards, like the wind swaths that we're showing here over Phoenix, Arizona. And finally, the machine learning-based probabilities, I won't go into those in detail. There is a small 5-minute video on our web viewer where you can learn about these. These take an event space where a storm or a line of storms cluster is expected to track over the next 30 minutes and plot the probability that a local storm report will be received per hazard type. A way to break it down is just think always as you're using WoFS, what product am I looking at, what is the duration, and what's the neighborhood. So another quick example to, again, illustrate what it means to make a probabilistic prediction of an individual storm. And you really do have to think of the individual storms and their life cycle when you're using WoFS. On the upper left, that's the observed reflectivity of this developing supercell, which had been around for about an hour prior to this model run. And this is something you can do in real time on the member viewer over here on the right, is kind of scroll through the 18 members, see how well they're initialized. In this case, it looks like they're doing a pretty good job initializing that storm, so we can have more confidence when we look at the output. And I picked a couple of the members and put them in motion there. And you see that they take that storm and make it a long-lived supercell with a gradual right-hand turn. In the middle, the probability of severe hail being reported is in the mid to high range and pretty good in location. But again, this concept of the farther out in time you go, half hour later on the right-hand plot, WoFS does even better with the track of that supercell and the intensity. And we were able to quantify this performance versus age of the storm in some work that Jorge Guerra led at NSSL and was published in Weather and Forecasting last year. Look at the left-hand side. This is the probability of WoFS detecting a storm in the right place at the right time over the next 3 hours. And the red trace is for any storm in the domain. So performance is really, really good. 70 to near 80% in the first half hour, dropping down only below 60% at 3 hours. But if we separate out and look at storms that had not yet initiated when the model run was started, the performance is much less spectacular at down around 40 or 50%, pretty comparable to other convection wound models. On the right-hand side, we see only storms that, yes, had initiated and were assimilated in the model. And you can see, like we've shown for the Michigan case and the Arkansas case here, performance just gets better and better if that storm has been around for 30 minutes or 60 minutes or more. I think another key concept here is that it's important not to give up on WoFS if it's not doing well initially, that it can recover from a poor early forecast. Switching gears a little bit, we've shown some pretty good examples of nice performance. I did want to remind ourselves that there are weaknesses to any system, and WoFS is no exception to that. So I've listed some of the more common failure modes. Here in the lower left, you can see the description of the 3 examples here. Environmental errors are probably number 1 in producing a poor performance. This is kind of an extreme example here where developing storms were analyzed as being just behind the dry line in WoFS. So WoFS dry line position was off just a little bit. That meant that the ensemble thought that these storms were in an unsupportive environment. It squashed them, whereas in reality, they became long-lived storms and with tornadoes on the southern member there. Just a few weeks ago, we had an example in the upper right of a narrow line of severe storms in Georgia that WoFS was completely missing. And they were simply too small, too narrow to resolve at 3-kilometer grid spacing. And in the lower right there, that's the December 2021 quad state tornado case in which WoFS was just unable to sustain that storm, whether it was maybe environmental errors plus a little bit of a resolution problem. So in the words of one of our test bed participants, WoFS is beguiling. It can look great, and you're getting this 5-minute resolution of the output. It looks like movies. And so you still have to obviously take a lot of care to examine the output and vet how well it's doing with an individual storm. Now, I did add this for today. I wanted to take a quick look at our run from Friday and the Mississippi event, because this is kind of similar, I think, to that December 2021 case in terms of a high shear, strong flow case with long track storms. And honestly, we don't have very many of those in our collection yet to understand just how WoFS should be expected to perform. And I would say that we did better here than we did with the December case. There were some signals, and you see one of the members there showing supercells out ahead of the line, tracking right through Rolling Fork, Mississippi. That member was an exception to the rule for this particular run, and this run only would have given about a half hour of lead time to that location. One of the signals that I am interested in, and we have a student from the University of Kansas who's studying some of this, is the environmental signal here. In this significant tornado parameter, we saw a very storm scale maximum value of over 4 in the STP, positioned right over the town of Rolling Rock. At the same time, WoFS did have in the mean solution there, the probability match mean contours showing what looks like a supercell in that location. It happened to be off in time, but could these kinds of signals at least point us to the location within the domain where the high impact event is possible? Pretty challenging thing to do in real time, but we need more of these cases and more research into how to use this kind of information. In general, when we're talking about other types of cases more commonly occurring, this is what we tend to see from WoFS in an idealized sense. I'm showing this September 2021 remnants of Hurricane Ida, which produced a series of supercell tornadoes over Pennsylvania and New Jersey. And very often in the early hours of a WoFS run, you'll get multiple signals spread across an area about the size of an SPC watch box. You go to 3-hour lead time, so the duration we're looking at is shorter, but we're also closer to the event time now. And the signal is really honing in on the Philadelphia vicinity as being the most likely to see tornadoes. And by 1-hour lead time, you sometimes get these highly confident small swaths of probabilities that are more on the scale of a warning. So in this way, WoFS is trying to bridge that watch to warning time frame and enable probabilistic predictions that are aided by numerical guidance on that scale. To kind of wrap up my portion here, I wanted to show several examples of how Weather Service offices have been using WoFS to influence their real-time products and services. And one of the most common is kind of in the middle of the screen here, this concept of a watch to warning graphic, whereas the SPC watch box comes out and then a little bit later, the WFO using mesoanalysis, but also WoFS, is honing in on the area that's most likely to see the threat within the next couple of hours. So I've highlighted the Kingfisher County, Oklahoma as the white box there to give you some sense of the scale. And so you have this watch to warning graphic comes out highlighting that zone of the state, and about an hour and a half later, the first tornado warning occurs down there in Kingfisher County. And so that's one of the more common uses right now. We also saw really fantastic use of the system for the derecho last May, which lifted northward through eastern South Dakota. At that time, we were chatting, Pat and I, in the Google chat room that we've set up for real-time WoFS conversations. We were chatting with the WFOs in that region, telling them the type of confidence that we had in the data based on all of our knowledge of the system. And that helped them to have confidence, in the case of North Platte, to bump up their wind speeds and add the WIA tags to their severe thunderstorm warnings. And then in terms of SVC, they cited several consecutive runs of WoFS supporting gusts as high as 100 miles per hour. The 103 knot spot max that we're showing there, that occurred within about 15 miles of where 93 knots was observed. So it's not just knowing that an event is going to happen. In a lot of cases, the wind speeds, there's some really good guidance coming out of WoFS. And then I love some of these QPF or heavy rainfall examples. So this is from the Weather Prediction Center in one of their mesoscale discussions, showing how you can actually incorporate some of this probabilistic language into your products, especially if you have a more technical kind of user, and they're talking to the WFOs primarily. But these are things they literally stated in their discussion on the right-hand side here, citing the different percentile products, the rain rates, and even specific timing. And again, it's that idea that I think WoFS is allowing folks the confidence to be a little more specific in the details at greater lead time. Finally here, another rainfall example. Later last year in August, we had one that was more tropical in nature, some Eastern Pacific tropical moisture, not very much instability, but the mid-afternoon runs of WoFS were able to latch on to the storms in Chavez County, New Mexico, and show that they would be very slow moving and really hit a bullseye of where this 8-inch maximum in rainfall actually occurred. There was also a false alarm signal. So again, each individual signal has to be kind of vetted, but the service hydrologist at the Albuquerque office was able to use this to lean on their emergency manager in that county and to lean on the River Forecast Center to get out better products and services ahead of a flood wave that came down the Pecos River. So a nice IDSS example. And then one final IDSS example here from the Masters Golf Tournament, WFO Columbia, South Carolina, used the lightning probabilities to catch on to this sneaky little storm that occurred out ahead of the main activity. In briefing emergency managers, they, in an indirect way, may have influenced getting the golfers and spectators to safety ahead of that storm. So as you can see, there are many potential applications of this. And on the right-hand side, you'll see we're exploring use with the Aviation Weather Center, fire weather test bed being spun up at the Global Systems Lab. And we've even submitted some proposals to get funding to dig into the winter problem. But really right now, my main task in life is to get the severe portion of WoFS transition to operations. So we're working to get that transition plan signed soon and to get more availability of the runs across the nation so more forecasters can get familiar with it. And so I'll just leave this page up here as we switch over to Pat's demonstration, but there's some contact information. And if you're not part of our Google chat room at your office, please check with your Sue. We'd love to see you in there in real time and have some of these conversations.
For now, we're switching over to Pat Skinner, who's going to give a demo of the WoFS webpage. Go ahead, Pat.
All right. Thank you, Jill, and thank you, Patrick. And so Patrick did a great job of covering a lot of sort of the principles of how we built WoFS, how we think it's useful, how it's being used, and I'm going to try to show some practical applications of some of that and just doing a short demonstration of one or two forecasts from an event last spring. So to begin with, just to navigate to the site, I normally just Google CB WoFS NSSL. That'll get you to this page, and then you can click on the new forecast one. That'll take you to our web viewer. As you can see, it's set up to our last run, which was last Friday. And so you can use these buttons at the very top to navigate to different dates. So we're going to go back to 2022 and May 17th. You then have different domains. That's not normally applicable now. In the future, when we run multiple domains in one day, that'll let you toggle between them. And then you can pick a WoFS initialization time. And you can see we generally run between 17 and 3 UTC with forecasts every half hour. We're going to go to the 2200 UTC forecast. And then you have the product menus that Patrick alluded to here. And as was mentioned, we have an enormous amount of products. And obviously for a forecast that we're going to produce every 30 minutes, it's not possible to go through all of these for every forecast. So I'm really going to highlight a few products that we view as foundational. They'll give you a broad sense of what the ensemble is predicting. And then the remainder of that information is there if you have time to do a deep dive or if there's a case-specific aspect of the forecast you're particularly interested in. But one thing that we found is that the reflectivity paintballs over 40 dBz are a very useful go-to product because they give you an enormous amount of information from the ensemble that you can then loop through very quickly. So this is now just any region within all 18 members where reflectivity is exceeding 40 dBz. You can see you have a couple of sort of random members in Southwest Kansas, but in general, you have this orangish-brown region in northern Missouri and Southwest Iowa, and that corresponds to an ongoing MCS that WoFS has initialized in the initial conditions. And so for looping through the different times in this forecast, you could use the slider at the top. One thing I found, though, is that it's difficult to get a smooth loop there, and if you want to change products, you end up accidentally changing the time. So one thing I really strongly recommend is using the greater than and less than keys to really quickly loop through any forecast. You can just toggle back and forth and zip through 6 hours of forecast time with 5-minute output very quickly. And when I do this, one thing that I think is neat and kind of novel to WoFS output is, as Patrick mentioned, you don't get a slideshow like you get with hourly output, you get a movie. You can see the growth and the evolution of individual convective storms. You can see things like these storms here in Kansas. They're growing larger. They're moving generally rightward compared to the rest of the members. And you can see a couple of them even split at the beginning. So you can identify things like storm mode between QLCS, supercell, single cells, etc. And also then a relative likelihood where you can see that you have a much higher cluster with these storms in northwest Kansas than you do in this area near Topeka. And so it allows you to really interrogate a lot of different aspects of storm evolution in a very rapid manner. And we know that we're under strong time pressure with a short-term forecast that's being issued every 30 minutes. So that's one of the reasons why we think this is a very useful product. One thing I forgot to mention here is that, the right side, we have a lot of interactive features that allows you to overlay different things. So I mentioned the keyboard shortcuts. There's a lot more keyboard shortcuts to explore. Some are more useful than others. I'm going to hit the greater than, less than keys the most. I'll show you another example in a little bit. We also have GIS overlays, so you can look at counties or NWS CWAs or roads. I'm going to leave the roads on for this case because it's useful to delineate the area near Topeka where you have this discrete convection initiation and supercell development. And looking at the actual evolution of this forecast, then you can see the propagation of the ongoing QLCS out of the domain. You can see the development of these supercells near Topeka, and then you can go all the way back to the 10-minute forecast. You can see there's really high likelihood of storms developing here in northwest Kansas. The reason for that is because there's storms ongoing at the beginning of this forecast period, and what has happened is WoFS has assimilated some radar and satellite data, and so it has incipient storms in the initial condition. However, they're not strong enough yet to be able to produce 40 dBz. That just happens in the first 30 minutes of the forecast. And then WoFS is also predicting CI in southwest Kansas. And then finally, there's this area that's coming in from west of the domain and moving through Nebraska. And the only thing I'll mention about that is that's something that WoFS is inheriting from older boundary conditions. So when you see storms that are entering the domain during the WoFS forecast, you can generally put less confidence that they're going to be predicted accurately than storms that develop within this forecast. And then going back to the results from Guerra et al., you can see that you have high likelihood of storms here and also a high confidence prediction of the evolution of this MCS in Missouri. You also have a pretty high confidence prediction of the storms in northwest Kansas, in southwest Kansas, and then a lower confidence prediction, just so you can see from the spread of the paintballs near Topeka. And so those are the main areas I was just going to look at. If you want to look at them in a different way, we can also look at the ensemble probability. And so instead of trying to guess at how many different colors are overlapping in a given paintball product, you can look at this probability feature at 15 kilometers here and get a sense that, yeah, it's very confident in the Missouri one, also in the Kansas ones, and less so in the Topeka example. And then finally, if you wanted to pick out a single member solution from a paintball, you can look at the member viewer. And if you zip through here, I'm just going to go out to Go2Z, sounds good, and point out that you can also use the M and N keys to really rapidly cycle through different members and get a sense of, what is the ensemble spread. You can see that you have, a lot of variation in terms of the location and sort of the coherence of this QLCS that's being predicted back in central Kansas. and then also in the coverage and location of storms here in eastern Kansas. And so with that, it gives you a sense of where the thunderstorms are expected. And so the natural follow-on is then which ones are going to be most severe. So what are the hazards associated with these thunderstorms? For that, I'm just going to look at mid-level 2 to 5 kilometer objectivity, which is a nice catch-all for all severe. And you can see that you have, this is the 90th percentile, and so, a reasonable maximum intensity being predicted by the system. And zipping through it, you can see that it really, in terms of objectivity, is defining the areas in northwest Kansas and then also the area near Topeka as having the highest potential severity during this time. And the last keyword shortcut I want to talk about is this is suggested by NWS forecasters last year, and it's been really nice, is we plot the 90th percentile, we also plot the ensemble max. And so if you hit the R key, you can toggle between those two and just be able to see that, okay, well, there's also a few members, although they're not overlapping, that are predicting really strong supercells down in southwest Kansas. You can see sort of this pockmark thing with the storms in north Kansas where we're predicting strong UH. And then you can see a broad region of just supercell development being predicted near Kansas. And if you want to convert that to probabilistic forecasts or the likelihood, you can hit the T button, and then that converts it to now the probability of exceeding 60 dBz using a 9-kilometer neighborhood. And you see the probabilities drop near Topeka, so you have, generally speaking, a low probability, high severity type event there, and a higher probability, high severe event with northwest Kansas. And so you can get the full breadth of the ensemble information just really quickly using these keyboard shortcuts. And what I'm doing now is hitting the R key again to cycle through different sized neighborhoods. The only thing I'll point out here is it's nice for capturing some of the spatial uncertainty. You can see the probabilities really increase near Topeka. And note that these neighborhoods are much smaller than those used in like the HRAP and other next day ensembles. Our goal here is to maintain some of the storm-specific information while also accounting for some spatial uncertainty. Okay, and so the last thing to look at real quickly is go back to the paintballs, is that we do provide real-time verification using MRMS. So this is now, the dark shading indicates where the observations in MRMS actually exceed 40 dBz. You go forward to a 45-minute forecast, you can see that you're generally on track with the MCS of Missouri, generally on track with storms that we're initiating in northern Kansas. And so, as would be expected, that's where we've assimilated radar and satellite information. That's where it's got the most accurate forecast. But you can see you have a pretty strong spurious signal for CI in southwest Kansas, and that's maintained through the forecast. The other thing you'll notice is that all the supercells predicted near Topeka, there's a pre-CI prediction. Those didn't pan out very well. You do get storms that develop there, but in general, they grew upscale into sort of this double-barreled bow echo you get across Kansas. And you can see the trailing bow echoes is somewhat well predicted, but in the later portions of the forecast, you get this merging of the spurious southwest storms with the northern ones, and you get a poor forecast of the orientation of that system. And so this is a nice illustration of how there's a mix of good and bad in every WoFS forecast. And the last thing I was going to show is just jump ahead then 1 hour. And once you get another hour of radar and satellite assimilation, you can see that there are issues that are still maintained, including spurious supercells near Topeka and the southwest Kansas one, but that extra information has really improved the forecast. So this is an illustration of how additional assimilation can basically correct initial errors in storm scale prediction and WoFS. And now you get, maybe not the best orientation on the trailing system, but you get a pretty accurate prediction even through 5-6 hours of these two systems as they move out into Kansas. And so that's what I was going to show. With the time we have left, we're happy to take any questions. Thank you.
All right. Thank you, Pat, for the demo. I think it's always really helpful to kind of see it in action. So I appreciate that portion. And so now we're open to the Q&A. I have one to start off with. We see in the other links section of this page things like tutorials and video overviews. Are there any publications or places folks can go to get kind of more information on how to use these tools?
Yeah, more information. Pat has a paper moving into the formal literature. I think it's Journal of Operational Meteorology, is that right? That tries to summarize some of these techniques and best practices with a really, forecaster slant to that material. We also have something we haven't advertised all that much is a case study page. If you go to the main WoFS page at the NSSL website, look on the right-hand side, you'll see case studies. And we don't have a lot of them on there right now, but they are pretty in-depth, the ones that we've developed. And my intent with that had some help with it from other scientists here, was to highlight certain products and how they might be used, just to give forecasters lots of different ways to think about how to use the system. And certainly when we get the transition plan in place, there will be plenty of training milestones, including a COMET training or WDTD training. And we've already been talking a lot with the science officers at their development course in Kansas City. So certainly that's something we're going to emphasize over the next few years before this gets to operations.
All right, thank you. Another question that came up is, you talked about testing simultaneous domains in the next year or so. Out of curiosity, do you know what maybe the extent of how many domains you'll be able to run in the future will be?
Yeah, so that's a topic that we will begin exploring this year. We're highly confident that we can run 2 domains at a time. Of course, the reason that we have limited domain size is the compute power needed to run this rapid pace ensemble. But in doing 2, we think we'll be able to catch those days with where there's multiple severe weather threats. We think that now that we've moved to a cloud-based system as of last year, and that's gotten even more firm with our architecture this year, that this cloud-based system, it's really just a matter of the cost of ramping up the compute power. And that's something that we'll want to work with the Weather Service to determine a concept for how to use this long term. Will it be like GOES mesosectors, or can we put a number of fixed domains across the country to run more frequently? There's a lot of possibilities there, but so we don't think we'll be stopping at 2 domains, but for now that's the short-term goal this year.
Thank you. Another one that came in is there a different link for WFOs that we can use to look at prior forecasts, for example, like IDA?
Yeah, the archived cases are cases from 2017 through 2021 before we shifted to the cloud, are all archived. And this is the old one, and you have the same date menu, so you can see we're up at 2021. There's the Mayfield case, and then the Duratio case from the 15th. I think we actually ran for the fire domain. But you can see, actually we don't have 2017 on there, but we have 2018, 19, and 20, including IDA. So you can navigate to the past cases using this. It's on our NSSL web server, so it is less responsive sometimes, but in general, it works pretty well for looking at past data.
Yeah, I'm glad that that question was asked, because it's a key point. You certainly don't want to be doing this for the first time or trying to learn on the fly during a severe weather event. Definitely encourage you to find a case on the viewer and go at it when you have some free time. Also, this link that Pat found on Google, if you go to the main NSSL WoFS page, you'll see links to our cloud-based viewer for the more recent runs, but there's also a link there for archive viewer, I believe. So multiple ways you can navigate to this.
Great, thank you. We do have a question that came in. It said, could you discuss the assimilation technique and frequency again?
Yeah, I'm happy to do that. It's based on an ensemble Kalman filter, and it's actually very similar to the HER data assimilation system as it's been applied since about 2021 onwards. We use a 36-member ensemble for the assimilation. We assimilate MRMS, radar reflectivity. We assimilate radio velocity from all the different ADAT sites that are interpolated to the WoFS grid. We also assimilate GOES cloud water path observations, which is a retrieved, basically integrated water product that looks similar to reflectivity, and clear sky water vapor, which will give you a sense of some of the mid-level thermodynamic properties. When available, we assimilate Oklahoma mesonet observations every 15 minutes, and we assimilate traditional observations every hour. And all of this is done every 15 minutes in terms of the remotely sensed observations. The goal there is simply to spin up ongoing storms in the model analyses as quickly as possible. We see that we have this very big difference in forecast accuracy once we have the initialization to be accurate. So, from our standpoint, in terms of improving the system, the faster we can put storms into the model, into the different members, the more useful and more accurate all of our forecasts are going to be.
Perfect. Thank you for that. A question that did come in is, are there any model updates planned for this year?
In a sense, but not really. For the most part, we'll be running the same configuration we have in the past. We've updated some of our observation processing. I think probably some of the biggest differences you'll see is we're updating the machine learning products that we're providing and hopefully providing them in a way that's more usable and combining all the different machine learning models into a single product. We've added a couple other features. They won't be on this case, but in the new ones. So let's just go back to the latest. So you can see a couple of the things that are in there. There's still some bugs to work through here, but you can see the different methods of looking at the machine learning products. You have additional overlays, so you can overlay the 0 to 2 kilometer UH paintball. That's actually something we found to be really useful. I'll just do it for severe wind here. And so like I say, they're bugs, but you can also see that the gray shading represents where the UH tracks are, which does not always represent where the broader object is for a given space. We're going to try to add some fire weather parameters. I think we have a low bias in our mixed layer cape, who we think is from a bug and where we lift our parcels from. We're going to correct. So I guess to make a long answer short, we're trying to correct a lot of little things around the fringes, but not with any major changes.
No, that's definitely helpful. Good to know. The next question that came in is, can mean photographs be plotted without having to go through the soundings toggle?
Not at this moment. And so one keyboard shortcut that is nice is V. You can do the sounding toggle. One thing we know is a limitation of the current system, and this is simply a function of computing power, is that it's not easy to pull up these forecast soundings. All of the images that make up the web viewer are generated prior to being viewed, so all it has to do is point to the right pings that already exist. If we were to plot all of the different forecast soundings, that creates as many images as all the other products combined. And so to save on computing expense, we process those dynamically, which is when you click on a point, it will generate these images, and unfortunately it takes a while. So it's a little bit buggy, but we will work to try to improve that.
Alrighty, a couple more have come in too. Does WoFS struggle with high shear, low cape scenarios compared to normal shear cape events, especially pre-initiation? Similarly, do strong forcing versus weaker forcing events change performance?
Yeah, no, that's a really good, really relevant question. I think we still need to do more research into the high shear, low cape environment. We don't have very many samples there. For instance, I showed in the talk today the December 2021 case, and I showed the rolling fork, the city case. Although they are high shear, they're kind of different environment. So we need more cases, as a short answer. You want to expand on that?
Yeah, just some very broad generalizations, but as what I like to think about WoFS performances. One, and Patrick mentioned this, is it does scale with expectations of forecast difficulty for a human. So for a low cape high shear QLCS, and you're trying to predict pretty rapidly evolving spin-ups within that, that's a difficult forecast for a human, and it will be for WoFS as well. It's simply a smaller scale, it's more rapidly evolving, there's less information to be able to read into the system to be able to predict it well in advance. So it doesn't mean the system can't provide useful information there, but in terms of bulk quality of forecasts, it will probably be less accurate than like a big discrete supercell in the plains with high cape. The other thing I'd note is that we've quantified that WoFS does worse through CI because it doesn't have information to create an accurate analysis of an ongoing storm. And so there's sort of this pre-CI versus post-CI delineation in forecast quality. Another thing that I think exists, and we're trying to quantify with research now, is small storm, large storm. And this gets back to the resolution limitations that Patrick noted. And so one thing that we noticed, especially for the December 10th Mayfield storm, is WoFS was unable to maintain that storm using 3 kilometer horizontal grid spacing. However, when we reran it with 1 kilometer grid spacing, it created an accurate forecast. So there was not a small storm, and it wasn't a moderate cape environment, but it wasn't a large storm either. And so we think that there might be some threshold in storm size where you can expect there to be a pretty rapid decrease in WoFS forecast accuracy, at least until we're able to run at higher resolution.
Thank you. Yeah, no, it's always good to know the limitations of the system as well. So thank you for that. Another one that came in is, we kind of touched on this a little bit with the multiple domains question, but what is the end goal and realistic time frame of WoFS coverage? Will every WFO be able to see it for every event at some point in the future?
This is a difficult question, but one that we hope to make progress on this year. We're going to be having a number of conversations with folks at NSSL and Weather Service headquarters to get a handle on a game plan to design a concept for how we want to use the system. We're exploring it in so many different ways, and we're even talking with the Aviation Weather Center about potentially setting up a domain that would stretch from Chicago to New York to test ideas for how to use this for aviation. We've thought about the possibility of having a fixed domain over Florida to support rocket launches for NASA. There are lots and lots of possibilities. So now I think is the time to converge on, out of all those possibilities, what do we actually want to do with the system? One could conceivably set up a CONUS scale WoFS. It would just cost a lot, and if you're going to run it every day, for all these different hazards, fire, weather, and everything, I mean, we feel it might be overkill to do that. This is the time, though, that we'll begin to answer those questions, and a realistic time frame for pushing what we've got, which is a couple of domains that can be repositioned like the GOES mesosectors, would be to get that into operations by about 2027 or 2028. One of the issues there is that we have dependency on getting our initial and boundary conditions. Right now, they come from the HER and the HER data assimilation system, as well as some GEFS influence on our boundary conditions. But moving forward, the RRFS is slated to go into operations, and so we would need to work on how to incorporate that operational feed into running WoFS. So there are a number of technical issues, and we likely wouldn't be able to be in operations until the RRFS gets settled. But that could happen as early as 2027, 2028. The good news is that between now and then, it's our intent and our hope that there will be this joint effort to provide more domains and more training so that forecasters get the kind of reps they need to become comfortable with the concepts so that this brings to operations.
Yes, absolutely. And to kind of build on that, the next question that came in was, what criteria do you use to determine when to run WoFS? Is it only Monday through Friday? Do you focus on any particular type of severe weather?
Yeah, great question. Traditionally, we have run Monday through Friday in the month of May to support the hazardous weather test bed activities, and we'll be doing that again this year. Over the last couple of years, we've begun to spin up more of these early season runs to try to catch cases like we had on Friday and to study those, but also to get the system in good shape to be able to run during the test bed in May. We hope that with our new cloud-based system, it runs very efficiently. Once we get all the development work finished with it that we've been doing this winter, that it should be fairly seamless to order up a run at any time of year if there's something worth studying. We know that the availability of domains is one of the hurdles to getting buy-in at the local level in the Weather Service for using this tool. And it's our intent to run more frequently going forward. But at this point in time, if we're outside of the test bed season, it's kind of an internal discussion. Certainly we get a lot of requests popped into our Google chat room, and we just kind of evaluate those based on research goals and funding to see what we can do. But we try to accommodate as many requests as we can.
All right, thank you. For those that want to stick around and look at some of the machine learning products, I think Pat is able to go through some of those.
Yeah, I realize I navigated away, so let me go back to the 2200 forecasts. And then really quickly, so we have lots of different products. So one thing that's been developed mainly by Monty Flora and Corey Potvin and some others is looking at machine learning products. And what this does is this is going to incorporate all of the WoFS guidance and WoFS only guidance only, but it's going to use it then to predict specific hazards and provide probabilistic forecasts of those hazards. So I'm going to look at hail because I think that was a neat one in this case. Using the logistic regression model, there's different machine learning models that are applied to these. What we found is that the simpler ones, at least in these cases, have actually performed as well as more complicated or newer methods such as random forests. But what you get is you get these blobs that you can step forward in time, and they represent basically objects where you have overlapping updrafts predicted in WoFS that have been identified using the enhanced watershed method, and then you have a probability of a severe LSR being predicted within each blob. And one thing that I think is neat is because this is very much a black box, you just have this really amorphous thing here in southwest Kansas with a 30 on it. And so it's showing you that, okay, well, there's a pretty strong possibility for severe hail in this region. You can notice some things right off the bat, that is the size of the object absolutely plays a role in what the probability of severe weather occurring in it is. And so it's relatively large, so you know that's controlling some of that 30%. But you can also click on that and you'll get this interpretability graphic. And what it shows is 5 of the main input variables we provide to the machine learning model and the distribution across all of our training cases, and then where the values for this particular object stand in that distribution. And a lot of times you can use it to infer some of the reasons for why the probability is the way it is. And just stepping through this, you can look at the 3 to 5 kilometer max reflectivity. It's basically right at the mean. Same for ensemble mean updraft, same for the size, maybe a little bit high on the major axis length. But what you notice it is a little bit outside of at least the interquartile range is the ensemble mean composite reflectivity is on the low end compared to most cases, and the ensemble mean 0 to 3 kilometer lapse rate is on the high end. And so what you can infer from this is that you have a very favorable environment for large hail prediction, given by the 0 to 3 kilometer lapse rates. But the ensemble mean composite reflectivity is saying that basically WoFS members are not predicting storms in the same area, and that brings down the mean. And so you have a conditional threat here, where the environment's favorable, but you have lower confidence in the fact that there's going to be a storm in this area. But if there is a storm in that area, you can be much more confident that it's going to produce severe hail. So that's the kind of thing that we hope you're able to glean with these interpretability graphics. I know Monty's always working on these and updating even what the full products are going to look like for the coming spring. So our aim for this is always to make it interpretable, to open up, you can infer the reasoning why the probabilities are the way they are, but then also to have something that's very easy to step through and glean hopefully some useful information from.
All right, great. Yeah, I think it's nice to show off the latest and greatest kind of products as well. So thank you for doing that little extra demo. So we had a great discussion today, a lot of questions asked. Thank you all for joining and making this an interactive session. Thank you to our speakers, and have a good rest of your day.
All right. Thanks, everyone.
Yeah, thank you. Good questions.